Hey guys, we are going to go over this distance time graphing assignment that you are doing at home. So what we're going to accomplish today is that we're going to do these three graphs, and then we're going to be doing the story problems all the way up through here, okay? If we look below 8 through 13, you'll finish that up on your next virtual day, okay? So use the table to draw a graph. Answer the questions in complete sentences. So I'm not as concerned about these complete sentences as I am with you drawing this graph and interpreting what's happening. Okay. So Addison is running in her neighborhood. Graph her time and distance. So we have it in a data table here. So these are ordered pairs. This is X and Y. Time is the X-axis and distance is the Y-axis. So 0, 0, her origin, where she started, and then 5, 15. All right, so the 5, and if I look at the seconds, those all are going to fit beautifully. But I look at my y-axis, and I see that's going up by 10. So I'm going to go ahead and mark those in between because I see that I am not necessarily going to have ones that are simply 20, 40, and 60. Okay, so 5, 15. So 5, and then I'm going to go halfway between 5 and 10. So 10 and 30. And then 15 and 45. And then 20 and 60. Okay, so I'm finished with plotting my points. Now I'm ready to draw the line in the order that I plotted them. So I'm connecting those all together. So I'm ready to answer the questions. Look at the graph. What can you determine about Addison's speed as she runs? So we have to remember, what does it look like with a distance time graph with a completely straight line like that starts out from the origin and moves up? Well, she is running at a constant speed. This is what on a distance time graph, what constant speed looks like. Okay, so she's running at a constant speed. Alrighty, so what is her average speed? Well, with my distance speed time triangle, I am finding her speed. So it is distance divided by time. Okay, what was her final distance? 60. 60 what? Meters. 60 meters. What was her final time? 20. 20 what? 20 seconds. So I'm going to divide that out. 60 divided by 20 equals 3. I can't cross anything off, so I have to use both of them. Meters per second. So ready for our second graph. Jill is riding her bike. Graph her time and distance. So once again, time is our x-axis and distance is our y-axis. So I'm quickly looking at my information I need to graph, and I see that the seconds, those are exactly what I need. I'm going to come here. It's going up. I just see 300, 600, 900. So I know that it is going up by 150. So I'm going to go ahead and put those in because that's going to help me visualize my graph, okay, and plot the points correctly. So now I'm ready to go. 0, 0. That's our origin. That's where she starts. So 5, 50. So 5 and 50. That's not very far, is it? Right here. And then 10 and 150. 10 and 150. 15 and 400. 15 and 400. About right there. 20 and 1,000. Right up there. So now I'm ready to connect my dots. Okay, so I'm going to connect them in the order that I plotted them. All right, so look at the graph. What can you determine about Jill's speed as she rides her bike? Well, on a distance time graph, this means she's speeding up. Okay, this is what it looks like when we're at constant speed. This is what it looks like when we are speeding up. So she is speeding up. And when we talk about acceleration, we call this positive acceleration when she is speeding up in the forward direction. So positive acceleration. Okay, what is her average speed? All right, so we know that speed is distance divided by time. What was her final distance? Was 1,000. 1,000 what? 1,000 meters. What was her final time? 20. 20 what? 20 seconds. So I divide that out. 1,000 divided by 20 is 50. 50 what? Meters per second. Okay, so I'm going to jump over that one. And I'm going to come to our first story problem. A baseball player throws a baseball. The ball travels 35 yards before landing on the ground. The ball stayed in the air for 3.8 seconds. What is the average speed of the ball? All right. So when I've got my distance, time, triangle, speed, time, triangle, I'm trying to find speed. So my formula is distance divided by time. All right. So what was my distance? 35 yards. And what was my time? 3.8 seconds. So I am going to put that in my calculator here. So 35 divided by 3.8, and I come up with 9.2. I'm going to just use one decimal place because if I look at how my other decimals in my problem are being shown, it's just showing one decimal place. So I'm going to have my answer be with just one decimal place. So 9.2 what? 9.2 yards per second. Okay, so you are free now. You're going to find speed with this one, and how long, that's going to be time. All right, and then this next one is also going to be time. So you are free to jump off of this teaching video to tackle this last graph and then these remaining story problems for today, or you can stay with me and we will finish this up together. Your choice, okay? All right, so let's go ahead and look at this last graph. Frank is skateboarding at the park. Graph his time and distance. So we know that time is X and distance is Y. So we're going to put that in there just like that. So we're going to start with our origin, 0, 0. That's our starting point. So I'm ready now to, I look at my time. So 5, 10, 15, 20. That looks great. I'm going to be able to plot that perfectly. But if I look at what I need to graph for my distance, that doesn't really fit perfectly. So I know I need to fill in these. Looks like I'm going up by 7s. So I am going to get those put in so it's easier for me to graph when it's time for me to graph, okay? So 0, 0. So 5 and 30. So 5 and 30. So it's going to be a little bit right in here. Okay, so 10 and 40. 10 and 40. And then 15 and 20. And then 20 and 0. Okay, so I am ready now to draw my lines in the order that I drew my lines. Okay, alrighty. So looking at the graph, what can you determine about Frank's speed as he skateboards? Well, this right here, he is going at a constant speed because it's a nice straight line. This we're slowing down. And here we are running at a constant speed. Once again, because it's a nice straight line, but he's returning back to this origin, back home. wherever that is, okay? All right, so he is moving at, he's moving at a constant speed. And he slows down. And then he goes as a constant speed again. Back home. All right, so describe Frank's motion after 10 seconds. All right, so let's take a look at that. Where is 10 seconds? Okay, so what's happening here? All right, so here's our 10 seconds. So now we're really looking at this right here, aren't we? So what is he doing during that time? He is returning back to his starting point. So whenever we have a distance time graph and our graph returns back to the x-axis, then we're returning back to where we started, returning back to his starting spot. Okay? All right, because at that 10 seconds, when we looked at 10 seconds, this is what was happening. At 10 seconds, he was returning back home. Okay? All right. All right, so let's take a look at another story problem. After scoring a touchdown, the Billies lined up for the kickoff. The kicker kicked the football 60 yards deep into the end zone. The hang time on the ball was 8.5 seconds. What was the average speed of the ball? All right, so we know that speed equals distance divided by time. What was our distance? Our distance was 60 yards. And what was our speed? Or our time, time, 8.5 seconds. All right, so I'm going to put that in my calculator. 60 divided by 8.5. And I come up with a number that looks like this. There's quite a few decimal places, okay? And it goes on and so on and so forth. So I know that I want to leave it, since this is in one decimal, I want to have this in one decimal. So this I am going to round 7.0. Is it going to stay a 0 or round to a 1? So I look next door, it's 5 or higher, so it's going to be 7.1. 7.1 what? Yards per second. Okay. If we are traveling 70 miles per hour on a trip from Austin to Dallas, which is 210 miles away, how long will it take to get to Dallas? Assuming we can drive straight there and there are no traffic delays. So how long? That's time. So what is our formula for time? Distance, speed, time. I'm covering up my time, leaving me distance divided by speed. Distance divided by speed. So what is my distance? 210 miles. And what is our speed? 70 miles per hour. So I divide 210 divided by 70, and I come up with 3. Comes out nice and even. Now I'm ready for my units. I have miles as on top, and I have miles on the bottom, leaving me 3 hours. So how long is it going to take? It's going to take 3 hours. Your grandma is following behind you on your trip to Dallas, but she refuses to drive faster than 60 miles per hour. All right, so let's change our color here. If she drives at that speed for the entire trip, how much later will she arrive in Dallas? All right, so this is a multi-step question. First of all, we need to figure out how long is it going to take her to get to Dallas. We already know how long it's going to take if we go 70 miles per hour. But what if we only go 60 miles per hour? The distance is the same. We are still going to Dallas. So that is still 210 miles away. But our speed is different. 60 miles per hour. So I am ready to put that into my calculator, and what I come up with is 3.5. 3.5 what? I've got miles up here, I've got miles down there. My answer is hours. So it's going to take Grandma 3.5 hours to get there. That's not what the question asked, though. The question asked, how much longer will she arrive in Dallas? So I'm going to compare 3.5 hours to 3 hours, and it is going to take Grandma 30 minutes or a half hour longer to get there. Driving 10 miles per hour slower. So that is what we are going to accomplish on today's virtual day. And next virtual day, we will continue with the remainder of those problems, okay? All righty, have a good day, guys. Bye.